and welcome to this hands-on session on calculation and interpretation of parametric tests. In the previous session, we have discussed the different parametric tests, t-test, z-test, ANOVA and correlation. In this session, we will see how to calculate them using data. By the end of this session, you will be able to compute the parametric hypothesis tests using statistical software and interpret the results in context of your research. We will be using the SPSS software for most of the tests. SPSS is a licensed software and you may have the license for it in your college or research lab. But for the practice, you can also use the 14-day trial version of SPSS, which can be downloaded on your laptop. Let us start with the z-test. As you know by now, the z-test is done when the population standard deviation is known and the variable is in the interval or ratio scale. There is no direct command for doing a z-test in SPSS, as we don't usually get data where the population standard deviation is known. However, for academic interest, let me demonstrate how it is calculated. Before we go on to the actual calculation, let us see how the z-statistic is actually calculated. It is calculated using the formula z equal to x bar minus mu divided by sigma by root n, where x bar stands for sample mean, mu is the population mean, sigma the population standard deviation, and n is the sample size. After calculating the z-statistic using this formula, the calculated z-statistic or z subscript calc is compared with the z-critical, that is obtained from a z-table like this, which is available at the back of any statistics book. When the level of significance or alpha value is taken as 0.05 for a two-tailed test, the z-critical value is 1.96. And for a one-tailed test, it is 1.64. When level of significance or alpha value is 0.01, the z-critical for a two-tailed test is 2.57 and for a one-tailed test is 2.32 and so on. After calculating the z-statistic of the given example, it is compared to the z-critical. And if the absolute value of the z calculated is less than or equal to the z-critical, then we fail to reject the null hypothesis. And if the absolute value of z calculated is greater than z-critical, then we reject the null hypothesis. So here I have a data set which is one of the sample data sets in SPSS named bankloan_cs.sav. This data set has the data of 1500 customers who have applied for a loan. And if you switch to the variable view, you'll be able to see the definition of these variables. It contains data like the customer ID, the branch ID, the age of the customer, educational qualification, their household income, amount of other debts they already hold, and also information regarding whether or not they have earlier defaulted. So here the label indicates 0 if they have not defaulted and 1 if they have defaulted. The type of scale used for collecting the data is also mentioned in this column titled Measure. So customer ID, branch ID are nominal or categorical data. Level of education is ordinal data, and the other data which are mentioned as scale are measured on an interval or ratio scale. That is, they are continuous variables. From this data set, I have already calculated the population mean and standard deviation for the customers who have other debts, reported in thousands, and found the mu to be 3.84 and standard deviation of 5.33. The problem here can be framed as: a bank manager claims that the average other debts held by a loan applicant is 3.84 with a standard deviation of 5.33. An analyst randomly selects 50 customers and finds a sample mean of 4.18. So the research question here is the average other debts of a loan applicant significantly different from 3.84? The null hypothesis H naught can be stated as mu equal to 3.84 and the alternative hypothesis as mu not equal to 3.84. What I have done now is I have randomly selected a sample of 50 customers from this dataset and created an Excel datasheet. Let me show you first how to import this data to SPSS. When you open SPSS, you will first have an empty datasheet like this. Go to File, Import Data, and choose Excel, and browse to the location where your data is located. For me, it is here. So I just double click on the file name or select it and click Open. Since I have multiple data sheets and I choose sheet 2 where I know my data is. I also check the box Read variable names from first row of data because I know that the first row of my Excel datasheet contains the variable names. Then click OK and the data gets populated in the data view of the SPSS datasheet. Now, we don't want so many numbers after the decimal point. So we go to the variable view and change the number of decimals after the decimal point to 2 for both the cases. Now we see that we have only two numbers after the decimal point. So I have created two data sets here, one drawing 50 samples randomly from the population and another created using a random number generator and not belonging to the population in our data set. We will now calculate the mean for both these samples, compute the Z statistic and compare it with the critical value at a 0.05 significance level. Also note that our hypothesis here is non-directional. Hence, we will perform a two-tailed hypothesis test. To calculate the mean in SPSS, go to Analyze, Descriptive Statistics, Descriptives. Select the variables from the left-hand side, so you can select them together by clicking the Shift button or select them one by one like this, and then clicking on this arrow, shift it onto the variables data box. Now click on Options. You will see that the mean, standard deviation, minimum and maximum are already checked. You can check the other descriptives like variance, range, kurtosis, skewness, etc. But right now, all we need is the sample mean. So we will keep that checked and uncheck the other boxes. Click Continue and then OK. The output box opens and we see that the mean values are given here. For the sample data selected from population, the mean is 4.18, and for the other randomly generated data, it is 5.70. Now, let us calculate the Z statistic for the sample data from the population using the formula. We get the Z calculated as 0.45. We compared this to the two-tailed Z critical value at alpha of 0.05, which is 1.96. And since the absolute value of Z calculated is less than Z critical, we fail to reject the null hypothesis, which means that the average other deaths of a lone applicant is not significantly different from 3.84, which is expected since we drew this sample from the given population. Now, let us calculate the Z statistic for the randomly generated data using the formula. In this case, the Z calculated is 2.46, and since Z calculated is greater than Z critical, our conclusion is that we reject the null hypothesis, which means that the average other deaths of a lone applicant is significantly different from 3.84. The same can also be calculated using MS Excel. In MS Excel, we can calculate the mean value for the data set by using the average function. So in any empty cell, type equal to average and select the range of values from your data sheet. Close the bracket and click and press enter. Now you see here that the average is calculated. The same can be done for the other data. After calculating the mean, you calculate the Z statistic and interpret the results after comparing with the critical values as we just did. Let us now look at how to compute t-statistics using SPSS. As discussed in the previous session, there are three types of t-test: one sample t-test, independent samples or two sample t-test, and paired samples or dependent sample t-test. Let us first see how to compute and interpret the one sample t-test. For this, we will take a portion of the previous data set, so that the sample size is less than 30. We will continue with the same research question as we did for the Z-test. For the t-test, we take 25 samples instead of 50 that were taken for the Z-test. I have prepared and saved it on my computer as the dataset2 SPSS data file, so I will just open that. Go to this Open File icon and choose the appropriate dataset from your computer. To compute the one sample t-test, go to Analyze, Compare Means and select one sample t-test. Select the required variable from the left side for which you want to do the t-test and send it to the right-hand side Variable Test Variable window. Then click on Options. Here you will see that the confidence level is by default mentioned as 95%. If the chosen alpha value for your test is 0.05, then the confidence level will be 95%. But if you want to have an alpha value of 0.01, then change it to 99%. For alpha of 0.1, it will be 90% and so on. In this case, we will leave it at 95%, so click on Continue. Next, look at the test value. By default, the test value will be set at 0. Change it to the population mean against which you want to compare your sample. For our computation, the population mean is 3.84. So, I will put that in here and click OK. The significance of the two-tail test is calculated here as 0.776, which is greater than the alpha value of 0.05. Hence, the conclusion here is fail to reject null hypothesis. We now do the same thing with the other sample and see what the conclusion will be. Again, click on Analyze, Compare Means, One Sample Test, and now instead of this data set, we will use this. The options remain the same. We are still working with a confidence interval of 95%, and also the test value remains the same. So we click on OK. The output in this case shows the significance level as 0.001, which is less than 0.05, and hence the conclusion will be reject the null hypothesis. Next, we turn our attention to the computation of independent samples or two-sample t-test. For example, if we want to compare the mean scores in statistics test between psychology students and law students, here the null hypothesis is stated as there is no difference between the mean statistics scores of psychology students and law students, and the alternative hypothesis is stated as there is a difference between the mean statistics scores of psychology students and law students. We have the scores for the psychology and law students in this data set 3. Here, the statistics scores for 100 students is given, some belonging to psychology and some belonging to law. The variable view shows that the test scores variable denotes the statistics test scores of the students, and std_type denotes the student type, that is psychology or law. Further, if you click on the values for student type, you will see that the data is labeled as 0 if they are psychology students and 1 if they are law students. Now that the data is ready, let us compute the independent samples t-test. For this, click on Analyze, Compare Means, Independent Samples t-test. Choose Statistics Test Scores as the test variable and student type as the grouping variable. Define the groups. Group 1, 0, which means psychology students, and group 2, 1, which means law students. Then click on Continue and OK. Before we click on OK, let us also look at the options. Change the confidence interval if you wish to. I will leave it at 95%. So everything is in order. We continue and then click OK. In the output table over here, we see two parts. One is the Levin's test for equality of variances and the other is the t-test for equality of means. If the p-value of the Levin's test is less than 0.05, we have to use the unequal variance result. Here, the p-value of the Levin's test is 0.447, which is greater than 0.05. Hence, we can assume that the variance of two groups are equal and check the t-test significance for equal variances assumed, that is, the first row. The t-test significance here is 0.778, which is greater than 0.05. Hence, the conclusion is reject the null hypothesis. Let us now look at an example of paired samples or dependent sample t-test. For example, to test if there was a significant difference in the average maths test scores of a group of students before and after revision classes were conducted, we state the null hypothesis as there is no difference between the mean of the maths scores of students before and after revision classes, and the alternative hypothesis states there is a significant difference between the mean math scores of students before and after revision classes. Let us examine the data in data set 4, which gives the scores of 35 students before and after revision classes. Go to Analyze, Compare Means, and Paired Samples t-test. Choose the variables you want to compare. In this case, my variable 1 is scores before the revision and variable 2 is scores after the revision. So I choose and click on the arrow to move them to the appropriate places. Then go to options. Everything is in order. So continue and click OK. The output shows that the mean scores after the revision classes have increased from what they were before the revision classes. It also shows that there is a strong significant correlation between the before and after scores, indicating that in general there was a positive impact of the revision classes on the test scores, and on an average those who got higher earlier also got higher scores after the revision classes. The paired sample t-test gives a p-value of 0.000, that is much less than 0.05, indicating that there is a significant difference between the mean math scores of students before and after revision classes. Hence, the conclusion is to reject the null hypothesis. Let us now move on to the one-way ANOVA test. For this, we will take the sample data set in SPSS, which is employee-data.sav. Here, we are doing a one-way between groups ANOVA. The alternative hypothesis here is that there is a significant difference in salary among the three groups of job categories. There are three job categories in this data. 1 clerical, 2 custodial, and 3 manager. To perform the one-way ANOVA in SPSS, we go to Analyze, Compare Means, One-way ANOVA, and then choose the current salary as in the dependents list and the job category or the employment category in the factors list. We then go to the options and choose to include the descriptives, the homogeneity of variance, and the means plot. Click on continue and then OK. The output shows that the test of homogeneity of variances is significant, which rejects the null hypothesis that the variances of the three groups are homogeneous, which is a key assumption of the ANOVA test. So here we actually need to do a non-parametric test, which we will do next week. For now, let us assume that the variances are equal and look at the ANOVA table, which shows that the variance in the means between groups is significant, thus rejecting the null hypothesis that there is no difference in the group means across the three categories. If we look at the mean plot, we also see that the mean of current salary drawn by the clerical is lower than that of the custodial, and which is much lower than that of managers. For the two-way ANOVA, let us look at the same data set, that is the employee-data.sav, and calculate the ANOVA across two groups, gender and job category. For this, go to Analyze, Generate Linear Models, Univariate, and add current salary as the dependent variable. Gender and employment category as the fixed factors. Go to Plots and choose Gender, the one with the lesser number of categories, as separate lines, and employment category or the job category in the horizontal axis. Then add it to the plots. Click on Continue. Click on Options. Choose the Descriptive Statistics, Estimate of Effect Size, and Homogeneity Tests, and click Continue and then OK. If you look at the plot here, you can see that there is definitely a difference in mean for the different job categories for the different genders, and in fact the difference is higher at the managerial level than it is at the clerical level. If we scroll up and look at the Levin's test for homogeneity, we see that the Levin's test for homogeneity of variance is violated. However, let us look at the between group effects. We see here that all between group effects are significant at a less than 0.05 level of significance. Hence, the null hypothesis that there is no difference in means between the groups is rejected. The last column here shows the partial effect size of the variables, and it shows that the interaction of gender and job category has a 3% effect size on the dependent variable, which is salary. Let us now come to Pearson's correlation and ask the question, is there a linear relationship between educational level and salary? Using the same data set, we go to Analyze, Correlate, Bivariate, and choose the variables education level and salary. Here, by default, the Pearson's correlation is selected. Click OK. The results show that there is a significant linear relationship between educational level and current salary. The correlation coefficient, Pearson's correlation coefficient, is stated as 0.661, and we know that if the Pearson's correlation coefficient is greater than or equal to 0.7, we can call it a strong correlation. In this case, it is a positive correlation, which means that the salary increases as the educational level increases. This is marginally lower than 0.7, so we can consider this correlation as a strong correlation, and it is also significant. So this is a significant linear relationship between educational level and salary. With that, we come to the end of this hands-on session on calculation and interpretation of parametric tests. Do download the SPSS trial version, or if your college or university lab has the licensed package, practice on it and let me know your questions. Thank you and happy learning.